Okay, we've derived the force for one particle hitting the right side of the wall. And so if we want the pressure, again, that's the force over an area. Force is mu1x squared over a. And our area is b times c, right? So it's the other two distances. We defined that in the last video. Or we can write this as mu1x squared over a, b, c. But if we take a times b times c, that's just equal to the volume. So we'll have mu1x squared over v. So we've got a pressure now. Now that's for one particle. We'd like to scale this up to an arbitrary number of particles. So if we have capital N particles, which is a notation we will commonly use throughout thermodynamics, this is some very large number, something like maybe Avogadro's number. Our total pressure is just going to come from all those individual particles hitting the wall, right? So P total is just going to be equal to P from particle 1 plus P from particle 2 plus P from particle 3, and then we can keep going until we have N of these values. All right, so we can rewrite this in summation notation. We'll use J to keep track of our particle number and say P sub J. And all these are going to be the same, right? So we can say the sum of J equals 1 to N of mu jx squared over V. M is, we're assuming we have all the same particles, same particle type, right? They're all nitrogen molecules or hydrogen or whatever. And we can factor that out of the summation since that doesn't change for any of the sums. Then we have our sum over all the different velocities. Now all these particles are not necessarily going to have the same velocity in the x direction. If we have a random distribution of particles. So we can't simplify this further at this point. Now we can't actually keep track of all these particles, but let's say what we can do instead is say we know the average, or say we can calculate the average. And that's what we're going to do with this is find the average. So if we know the average of the velocity squared, this ux value, we can write that as ux squared. Now this is not necessarily something we know, but what we can do is we can take our model here, write this in terms of an average velocity, and then take experimental data that we have, the ideal gas law, to find out what this value of ux squared is, this average ux squared. Okay, now let's just go with what's the definition of an average. An average, right, the average value of ux squared is we add up all the different possible values of ux, not all the different possible ones, but all the different values of ux squared, and then we divide by the total number of values, right? That's how we define an average, is you add up everything, divide by the number of things that you added up. Okay, so we can rewrite this to express this sum in terms of the average, so that we don't have to deal with this sum anymore. So it's just going to be big N times the average velocity in the x direction squared. So then we can take our P total equation and say that it is equal to m over v times big N ux squared on the inside, the average of the square of the velocity. Or we can say PV equals m times big N ux squared average. Okay, now something you may notice, sorry about that, is that we're getting something that sort of looks like the ideal gas law here, right? We have pressure times volume on one side. We have N, big N. This is related to the moles, right? We could change this to be in terms of moles instead of total number of particles like we have right now if we divide by Avogadro's number. And so what we know is that everything else, what we have left must be somehow related to temperature, right? So the speeds of the particles must be related to temperature. And so we're going to continue this discussion in the next video, looking at can we find out something more about this average velocity value that we have here. And also think about, we've only done this for one wall, we need to expand this to all the dimensions, not just thinking about the x dimension.